Hello and welcome to this lecture. In this lecture, we are going to look at another type of problems, a set of problems which are quite typical in practice as a data scientist. You may meet these kind of problems everywhere data is being used, where there is a little bit of modeling and a little bit of estimation. So far, we never looked at the modeling thing. The model was given to you and you had to just find some unknown parameter in the model. In this case, you may have to think a little bit about the model itself and play around with some things, or maybe the problem is very big, large data, multiple models, multiple estimations, etc. Okay, so let's start looking at it. So here's a very common problem in an area called ecology, which deals with population of animals and all that. Okay, so this method is popularly called capture-recapture. Okay, so capture-recapture, there's lots of other terms for this. Capture-recapture is what I've seen at least as quite often used. This is a method that people use to estimate number of animals in any area. Supposing, for instance, you go to a lake and you know that there are turtles there, and you want to find how many turtles are there. Okay, how do you go about doing it? So here is what you do. So this is maybe not turtles, something slightly bigger. So you capture some subset of animals, whichever animals you can get, how many ever turtles you can get. Put some tag on them. It could be some paint or some mark or something that will never go away, and it can be easily identified the next time you do it. After you capture them, you release them. Okay, so remember, we are ecologists. We are not trying to hurt the animals in any way. So we try to make sure the tagging doesn't hurt them in any serious way. We capture some animals, tag them, put them away. Right. So they've gone back and then they're mixing up in the population. And a little bit later, you come back. And then again you do a random capturing of animals. Okay, random. First time also you randomly capture animals and tag them. Second time also you randomly recapture the animals and look at how many of them were found to be tagged. Okay, in this case, as it turns out, 50 animals are captured and 20 of them were found to be tagged. Okay, so from using this information, you have to try and come up with an estimate for the population size, the actual total number of animals, right? So you tagged 100 animals, there is some other m number of animals which are untagged out there, right? So when you come back and when you start pulling out 50 animals, some of them will be tagged, some of them will be not tagged. Okay, so this is an example of a hypergeometric type distribution, right? So you have n animals, let's say, n is an unknown parameter. Okay, so you came in and you tagged, so this is the big set of n animals, and you tagged a certain number of them, tagged, untagged. Okay, so tagged is 100, untagged is, I don't know, n minus 100. Okay, so after this, from here, you randomly select. So these are your assumptions. Your initial assumption is this 100 tagged or equally spread out over the entire range of area where you expect the animals to be. All these assumptions are critical. So you can't just go to one area, tag all of them there, then go to some other area and then recapture. Then you'll find something else. It's not correct, right? So it should be uniformly there. So randomly pick 50 from this set. Okay. So when you do that, you found that 20 were tagged. Right, so this is so number of tagged animals. So this is recapture, right? Recapture. After number of tagged animals in the during recapture. Is hypergeometric. Okay, so it is distributed as hypergeometric. So probability that the number of so let's say we call this m. So this m is hypergeometric. So probability that m equals 20, right? In the denominator you are going to have n choose 20. In the numerator you are going to have 100 choose 20 times n minus 100 choose 30. I'm sorry, 50 here, 20 and 30. So this is hypergeometric distribution. So the expected value of the hypergeometric distribution is 50 times 100 divided by n. Okay, so 100 by n times 50. So this is something you can prove. I'm not proving it for you. So this hypergeometric distribution has this as the expected value. Okay, so what we got is one sample from the hypergeometric situation, hypergeometric distribution. Right, so it's exactly just one sample from the hypergeometric distribution, and you found that sample to be 20. Okay, so what does the sample mean? In some sense, sample mean, if you have one sample, everything is very easy, right? Sample mean is 20, and how will you estimate the sample mean? Your best estimate for the distribution mean is 20. So if you want to estimate even ML estimate for n, you're probably going to do it's I guess let me not go to ML here, so sorry about that. So if you want to do method of moments estimate for n, you simply equate E of m to 20. So we can do a method of moments estimate, which is quite simple in this case. So you equate 20 to the distribution mean 50 into 100 by n, and you get your n. N is 50 into 100 by 20, and that will work out to 250. Okay, so your estimate for the total number of animals in that area is going to be 250. So notice how we did this. We saw we saw the process that was adopted, fit a certain distribution to it, and then did a method of moments estimate. You can say maybe I want to do an ML estimate. ML estimate is going to be a little bit more tricky, I think. I don't know. So you'll have to maximize this probability, right? This 100 choose 20, n minus 100 choose 30 by n choose 50. You have to maximize that over n. Maybe it's easy, maybe it's hard, I don't know. Maybe it will come out to be the same, I don't know. It could be something else. Okay, you have to maximize that over n if you want to do maximum likelihood estimator. It looks a little complicated. You can do method of moments. Method of moments is quite popular. 20 equals 50 into 100 divided by n, and then that you manipulate, you get your 250. Okay, so this is a simple example of how estimation is used in a very interesting way in this ecological problem, where you had this interesting way of capture-recapture method of animals, hypergeometric distribution, one sample from it, and estimating the unknown parameter n. Okay, hopefully this was clear. Okay, so here is another problem which is really very common, and this sort of involves estimating a Bernoulli P distribution. Okay, so notice what's happening. There is a new machine, and out of the 10 produced items, the machine produced some 10 items, no item was found to be defective. Okay, so supposing you have to estimate the fraction of defective items that are going to be produced by this machine. Okay, what will you say the estimate is? Okay, so somebody gives you a new machine, it's producing something, I don't know, nuts, bolts, chips, I mean something it's producing, and you saw it produce 10 things, and all 10 were good, nothing was defective. Okay, and supposing you have to now estimate the probability that this machine will produce a defective item, how will you do it? So I'm doing it in the machine world. This can be anything else also, right? This could be, some students are graduating from a college, and some company is coming to recruit them. Okay, so they start interviewing. They found they interviewed about 10 people, and they found nobody was good. Okay, so now what are the fraction of students who are good in that college? Okay, so such things happen all the time. There will be a fairly large population in this. So much more can potentially happen, and you can't look at everything. You're only going to look at some number, and you probably can see it in a sequence or something, and then invariably you may not see anything, right? And then in those cases, how do you go about estimating the fraction of defective items? In this case, I gave you a machine. There are some fancy things you can do. Supposing, for instance, there is a review for a product in some online portal or something. You find every review is good. There are only 10 reviews. All 10 are good. Do you like it? I mean, you want to say that there should be some doubt, isn't it? I mean, it's not like everybody is going to like it. Right? What's the probability that one particular person is going to like it? Maybe you want to estimate it slightly differently. So these kind of problems show up all the time. okay. The situation I put down is with machines and items and all that. You can replace it with anything else and you have the same problem, okay. So if you probably did not have any other information, it's tempting to say 0, isn't it? 0 seems to be a good answer. In fact, it is the maximum likelihood answer, right? So what is the situation I'm looking at? I'm saying I have n samples from an IID Bernoulli P distribution. So xi is equal to 1 if item I is defective, 0 otherwise. And let's say probability of xi equal to 1 is p, and my goal is to find p, right. So my n is equal to 10, it's fairly small, and supposing I observe the sequence 0 0 0 0 0 0 0 0 0 0, p hat, the method of moments, and the ML will tell you 0, okay. So this is a very typical answer. I mean, we know this is true, right? Bernoulli P is a standard example we've been seeing again and again. You do 0, 0, but this is not a believable situation in several cases. I mean, even though it looks like a fairly valid method, the ML estimate, you may not be very happy with it. The reason is you have some prior knowledge about these situations, right? So you may have your experience with, say, in the college example that I gave you. Even though 10 people didn't interview well, you may have a general knowledge of how good that college is relative to other colleges. You might have gone to other colleges where, there would have been a certain fraction of people who you have recruited before, right? So you know that it's not 0, it can't be that bad. So you have to sort of use those prior experiences and do something different here. So anytime you want to use prior experience or modify the estimation problem when you have very little data, using some other sources of information in some clever way, right? No, you're using something more than what's here, right? If you just use this, then there's no problem, but you have to use something else which is maybe loosely connected in this. How do you use it? All that you bring in with your prior, okay. So that's where the Bayesian estimation, at least in many people's minds, it scores really well. But some people say it's a different problem. I mean, you're giving me additional data. Then why are you asking me to do this, etc., etc. Anyway, so let's not go there. We'll just stick to how to use the Bayesian estimation here and do this. Okay. A very typical way to do it is to use a beta prior, right? So I'm going to say Bayesian with beta prior. I'll do prior with beta distribution, alpha, beta. I don't know what alpha is, beta is, but once I do this, I know that my beta hat base is going to be, summation xi plus alpha, maybe I'll write it a bit more, xn plus alpha by n plus beta. Okay, so now you start doing something interesting, right? So in this particular case, for this particular set of samples, this works out to alpha by n plus beta. So n is 10, so it's 10 plus beta. Okay. So now your choice of alpha and beta will start giving you some values for this p hat, right? Is it good? Is it bad? It depends on how you pick your alpha and beta. Is there some knowledge you can have? A very, very common thing is to use a prior which is non-informative. Okay. So one choice could be just to use alpha equals beta equals 1. So this is uniform, non-informative as a flat prior. Okay, people call it flat also sometimes. You put alpha equal to beta equals 1. So this makes the prior uniform distribution, right? So in this case, you get your p hat to be 1 by 11, right? Did I get that right? Yeah, alpha by 10 plus beta, you would get 1 by 11. Okay, so this would be like, I don't know, this is giving you roughly about 9%, right? Okay. So this is telling you 9%. Okay. So notice this is not too bad. Okay. So maybe this is reasonable. People like this alpha equals beta equals 1. If you don't know anything else, you want to use a flat prior, and if you use a flat prior, you suddenly get 9%. you go from 0 to 9%, okay, which is not too bad. Some people will say this is more of an interesting answer than 0, okay. Now look at the prior information that's given here. It says the average of the fraction of defective items was found to be 10%, okay, so that's nice. And the actual fraction was between 5% and 15% in 95% of the cases. So you've collected this data from other machines, other similar machines in the past. Maybe you've used it, or maybe somebody else has used it, put up this information, right? So you've collected this information from other machines in the past, okay? And what is generally known is that the expected fraction, the expected value for this fraction is going to be about 10%, okay? And between 5% and 15% in 95% of the cases. So it's a pretty decent machine. It doesn't go bonkers all the time, but it's between 5 to 15% in 95% of the cases. Now, the question is, you can always the question is how to pick alpha beta. You can go the non-informative route, or you can do, so I want the expected value to be 10%. So expected value of prior is alpha by alpha plus beta, right? That's something we know. This you equate to 10%, which is 1 by 10. Okay, so this will give you beta equals 9 times alpha. Okay, so this is different from alpha equals beta equals 1. That gives you an expected value of 0.5. Okay, do you really expect half the things produced by the machine to go wrong? Then you're in a different ball game, right? So you're talking about something else. So in this case, maybe beta equals 9 alpha is a better choice, right? Not only that, there's one more information that's given here: 5% and 15% in 95% of the cases. So if you plot the beta CDF, okay, PDF of beta alpha beta. Here is this 10% or 0.1, and it has to have something like this. It has to look like this. Okay, beta sort of dies from 0 to 1. We know that, and then this area, a large fraction of the area, should be between 0.05 and 0.15. If you take 0.05 and 0.15, this area should be 0.95. Okay, so 95% of the cases. So you use these two information. So find alpha and beta that satisfies this condition. Okay, it's an interesting little exercise, right? Beta equals 9 alpha, that's already given, and you have to find the probability that the point between 0.15 and 0.05, you have 95% probability. How do you find alpha and beta? That will satisfy this. If you do this, maybe you get a slightly better estimate for this guy. Now, so notice, if you put beta equals 9 times alpha, so your alpha, this is already becoming alpha plus alpha by 10 plus 9 alpha. So that's what you're going to get. So it's just a question of what the alpha is, right? So now how do we find this? You can use once again our tried and tested SciPy stats and all these things to see if we can figure this out. So now there is this beta distribution, and SciPy stats has it, which has a CDF function also. But you don't just want the CDF, right? It's between 0.05 and 0.15. Okay. So it seems a little bit crazy. So in these kind of cases, I like to do the following, just to trial and error, try various things to get something. So usually you can define so FB or something. I can call it anything that you like. There is something called this lambda function, which will let you do something very quick. So this is going to be, so A is going to be my alpha. Okay. For a particular alpha, I want to go to SciPy stats beta CDF of 0.15 comma 9 into A. I think that's okay. Minus st dot beta dot CDF of 0.05 comma a comma 9 into a. I think that's okay, but just to mention, make sure, I like to see that that's what people do. Sometimes some examples are given here. You can quickly check. I think it is just AB. Yeah, I think it's just AB. So it's good. So this is my function. So this basically defines a quick function for me. Or maybe I should put a bracket here just to be sure. Okay. So now I can try to evaluate FB of, I don't know, 3. Okay, so I'm going to pick alpha equals 3. I get 0.656. Okay, so that's not good enough. I want 0.95, right? So maybe I should go to 10. Okay, 0.91. That's still not good enough. Maybe I should go to 13. Now we are talking. It's 0.9475 is almost there. So maybe I should go 13.5. I'm going a little bit above, maybe 13.3, I don't know. That's good enough, 0.95000. So 13.3, at 13.3, alpha equals 13.3, the difference of CDF at 0.15 and 0.05 is 95%. So we can pick alpha equals 13.3, beta equals 9 times 13.3. This will satisfy both of these conditions. Okay, so I'm going to pick alpha equals 13.3 and beta equals 13.3 times 9. So this given these conditions, p hat is working out as 13.3 by 10 plus 13.3 times 9. Let's just go back to our wonderful calculation here. Print 13.3 by 10 plus 13.3 times 9. So that's going to give me 0.1025. So that's 10.25%. That's okay. 0.1025, which is 10.25%. Okay. So 10% roughly, it's quite close to the the average value that we had. It's not deviating too much from it. We're not allowing all that much variety in the prior. I think the prior is really strong. So but anyway, I think even if you put the uninformative prior alpha equals beta equals 1, you got 9%, 9-10%. It's okay. Okay, so I think these kind of problems are very reasonable. They show up quite often in data science in so many different ways. You have limited data, and then you have to use some knowledge from somewhere else and sort of influence it and use it in a prior and come up with better estimates. Okay. Okay, so the last problem I'm going to do is one of those bread and butter statistical tasks. Okay. It's a fairly largish problem, so I cannot quite do it on this. So I'm going to do it on the Colab sheet. Okay, so let me go to the Colab sheet that I have here. It's not this one. It's not my rough work Colab sheet. Maybe I should open it in a new tab. Okay, it's doing something else which I don't want. Okay, on statistics 2. This is the sheet that I've already shared with you. You have this Colab sheet with you. So I did some minor reorganization to okay, so let's just import all these things. Pandas and matplotlib. Okay, so we've imported the packages. Let me come back and show you this little problem, which I think is a really textbook problem, not textbook problem, very bread and butter statistical problem that you should be comfortable doing. So let's start by looking at it. Okay, so it's about fitting a distribution and estimating parameters when the data is given to you. Okay, so we need one more thing here. We need one data file which is about gamma arrivals, etc. So I have to put it into my workspace here so that I load it. So for that, gamma arrivals, this needs to go here. Okay. So remember this, so every time you restart your Colab, you have to do this, because I mean this disk is just not permanent, or you can put it in your drive or something and then mount it and do such things also. But anyway, I'm just illustrating it, so I'll keep it like this. So this gamma arrivals is a file that I have. Okay, so I've taken this exercise from the book Mathematical Statistics and Data Analysis by John Rice. I had mentioned this book earlier to you. It's in the form of an Excel file. You can go to the website of this book and download this Excel file also. That's what I've done here. So these are inter-arrival times in some gamma ray experiment. Okay, so I'm not keen on what the experiment is. So, but this data is available as an Excel file. So first thing you should do is, of course, upload it into your computer and then read it. For reading, I'll use this something called Pandas. Okay, so it's a very powerful Python package. It can easily read Excel files and give it to you in a Python data structure. Okay, so let's run that. It did it and it ran. It gave me one column of data, 3935 rows, 3935 rows. Okay, so you need a computer to process this. You can't do it by hand, absolutely. Okay. So the first thing you get is a sense of the data. You can get other summary statistics, but histogram to me is a very, very good way of capturing information about one type of data. You see what the data is, you get a rough idea of how it works, and look at this distribution. It has like a falling distribution. It's a lot of values, so we have to use a continuous approximation here. It's very easy to fit this. And then how do you pick what kind of function? The most interesting function that you can pick for something that falls like this is usually a gamma distribution. So gamma has two parameters. If you remember the gamma distribution, so maybe I should go there and write down something. Okay, so the gamma distribution, I described it a little earlier in one of the other lectures. It's the PDF is if x is gamma for beta, the PDF is beta power alpha by gamma alpha x power alpha minus 1 e power minus beta x for x greater than 0. So this is the alpha gamma distribution. This gamma function is some special function. We can assume it exists and you know what it is. So this is what it is. So if you sketch the PDF, it can look like so usually it sort of quickly goes up and then comes down. It can look different depending on the value of alpha and beta. It can look like this. So anything that falls off like this, you can do. For instance, if you pick alpha equals 1, it's going to just fall off like this, right? It gives you the exponential distribution. So it's very, very versatile distribution for positive numbers, and you can use it like this. So it's very commonly used. A couple of facts. Expected value of x is alpha by beta. Expected value of x squared is also well known. So in fact, I mean, in case you're wondering how is it that I would think of all this, so you can just go search for gamma distribution. So this is very, very common. Don't assume that I know all these things by heart in my head. I mean, of course, if I work on it for a little while, I'll remember it, but I'll also forget. So you just search for gamma distribution on Wikipedia, look at this information. Everything is here, right? So look at this. There's two different ways to parameterize it. Alpha, beta is what we're looking at. Mean is alpha by beta. Variance is alpha by beta squared. So all of these things are there. Everything is here. Even the moment generating function, everything is here. You can do various things. There's even like a method of moments, right? So it's all here. Look at the shapes, various shapes. I mean, everything is here. So there's no need to panic and worry. Of course, in an exam you won't have access to all this, but we will give you the necessary information. So don't worry too much about it. Okay. So we have samples. We have 3,935 samples supposedly from a gamma distribution, and we have to fit alpha and beta. So to find alpha beta for this distribution. Okay. So you could use method of moments. I've described here. This sheet is, by the way, available to you, so you can go in and look at it. I've described here the method of moments. Equating the first moment to alpha by beta and the second moment to alpha squared by beta squared plus alpha by beta squared, and you can solve it and you will get this answer. You can compute the values of m1 and s squared, which is sample variance, is m2 minus m1 squared, and you can do all this. Okay, so this is fine. So you can do the method of moments estimate quite straightforward, in a straightforward fashion. So that's what I've implemented here. I've taken the data to be DF. DF is something called data frame and pandas, and this column 1 was there, right? So you can see here, this is column 1. So I've taken that column 1 data and put it into a NumPy array. NumPy arrays are easy for us to work with, so just do that. In this case, it's enough. And M1 is the average of the array, okay, the average value of all the values. So that will be M1. And then this S squared, I've just called it SS as for convenience, variance of X. Okay, so it's a sample variance. If you want, you can do DDOF equal to 1 if you want the unbiased version. It's not too critical. You have 3,935 of them. Nothing will change significantly. So you can run this. You get your M1 and SS. That's done. And then you do your alpha hat method of moments, beta method of moments. It's M1 into M1 by SS, M1 by SS. You get your alpha and beta. Okay, so those are the two estimates. You see, this is very close to 1. This is quite small. Beta is very small. Okay. So one of the things, the first things to do after you find a fit, after you find an alpha beta for this, you have to plot it on top of the density histogram and check whether the fit is good or not. So here is a little plot. I've used the matplotlib functions. I've used scipy-stats to compute the gamma PDF and the NumPy to do the remaining. And you have the histogram and you have the gamma distribution on top with this value, right? So gamma distribution, I have put alpha and then scale is 1 by beta mm, and you get the fit. So you see the fit is really, really good, isn't it? So this gamma distribution is a very good distribution for this. Okay. The next thing you may want to do is confidence intervals, and for all of those you can do or find the bias variance of this estimator. You can do Bootstrap, right? So Bootstrap is something I described to you earlier in the context of geometric estimation in geometric distribution. So here we are doing gamma distribution, and so I've described the method here, how you go about doing it, and you can see the Bootstrap algorithm here, right? So n is 1000, I'm doing 1000 samples, 3935, I'm finding alpha hat, beta hat, I'm just storing all of those here. So just repeat it several different times. So this runs, okay? And then one good thing to do is to see the histogram of the Bootstrap simulation. Okay, so you got the alpha and beta in Bootstrap. So let's see how the histograms look, and you can do the histogram here. I've plotted it here, and you can see it's around this 1.01, right? So this alpha histogram varies from like 0.9 to 1.1. So it's good. It's showing it's not showing very high variance. Likewise, beta is between 0.011 and 0.014 or something like that, right? So it's good. It's not showing so much wide variation that they have to be alarmed. It's reasonable, okay? So also, the histograms are roughly normal, right? Even though the distribution is alpha, beta, I'm doing some crazy method of moments calculations, the distribution seems to be roughly normal, okay? So that's a good thing also. So you can find the variance, to get the standard error of the estimator, which is basically standard deviation. You can get that, and you see the values are pretty reasonable. For alpha, it is 0.03. For beta, it's 0.0004. So all this is pretty decent. Remember, the value alpha is like 1, around 1. So 0.03 is quite small. Value of beta is 0.012 or something, right? So that's what we got here. The beta mm came out to be 0.0127. Okay, so 0.0044 is pretty decent error for that. Okay, it turns out you can also do confidence intervals using Bootstrap. Okay, so the idea for doing confidence intervals in Bootstrap, the main idea is to find this delta 1 and delta 2, right? Right, you have this error, and for the error, CDF of the error is known. You can do this, but if CDF is unknown, you can find this using the Bootstrap. How do you do that? So if the CDF is tough, you can use the percentiles of the Monte Carlo numbers. So you take the list of numbers, alpha hat, mm1 alpha hat, you simply subtract, oh my goodness, what did I do here? This is wrong, 1.0123. Oops, sorry about that, this is a bug. It's okay. Where was I? Yeah. So you can just do this and then pick the percentile, 100 alpha by 2 percentile, 100 1 minus alpha by 2 percentiles, right? So this is one way. In a list of numbers that you produced according to the distribution, you want to find the proportion, right? Sample proportions, and that you can do with percentile. So you can directly, using this numbers, estimate delta 1 and delta 2. So this delta 1 and delta 2 estimation is just based on the Bootstrap itself. So you can look at this in more detail if you want. Hopefully it's clear to you. So I've estimated my delta 1 to be 0.061415 and delta 2 to be minus 0.0604. Okay. So the confidence intervals for alpha will work out as 0.9508, 1.0727. Okay, that's it. So that's so this kind of sequence of steps you should be able to comfortably do in any data. Given any data, if you think it had follows some distribution, you first do the histogram, see if it fits into any of the distributions, scale it, move it around differently, and then try and estimate the parameters using method of moments, or you can use even maximum likelihood, and you can even find Bootstrap confidence intervals, right? You can easily find the 97.5th percentile, 2.5th percentile, and find 95% confidence intervals using Bootstrap. So Bootstrap is such a powerful and versatile method. So maximum likelihood also can be done. It turns out for the gamma distribution, maximum likelihood is a bit painful. I've described it here. I'm not going to go into detail in the lecture. I will encourage you to look at it. It's possible to numerically solve for the maximum likelihood estimator, and you get a maximum likelihood of 1.026. 1.026, 0.0128. Okay, so you can also check the fit of the histogram. Both of them are really good. All of these are will work out very nicely for you. So then you can do Bootstrap. Even for the ML, you can do Bootstrap to find the variance. You see the variance here is it's actually significantly smaller than the variance we got for the method of moments, 0.01, 0.02, while we got 0.03 in the method of moments case, 0.0003, while we got 0.0004 in the method of moments case. So this sort of suggests that the ML estimator might have lesser variance and lesser, it is more dependable for that reason. Okay. Once again, I mean, you can go through this calculation of how I found the ML estimator. It has some numerical solution and all that. It's not very surprising. You saw in one example how you wanted a quadratic equation solution, right, for ML. So likewise for ML, you can have highly complicated numerical algorithms also for ML. It's not very straightforward and closed form all the time. Okay. So that concludes this this particular type of problem. So this last sheet I showed you is also shared with you. It's absolutely vital. Okay, this is the important skill in this whole area. You have a list of numbers which you think comes from a distribution. Look at the histogram, parameterize it. Think of some way of doing it. I showed you a continuous value. It could be discrete, in which case you have to come up with some other clever way of doing it, and see if you can estimate the unknown parameters for a good fit. And then you should be able to do confidence intervals for it. You can use Bootstrap. You might have to do numerical methods to numerical solutions to equations for finding the ML estimate if necessary. Okay, so this concludes the study of the point estimation problems. From the next lecture, we'll move on to another very important piece of analysis, statistical analysis, which is called testing or hypothesis testing. We'll start that from the next lecture. Thank you very much.